Hey, today we're going to talk about polar curves, by which I mean the graphs of functions described in polar coordinates. And just like in our regular Cartesian coordinates, the graph of some equation is the set of all points that satisfy the equation. But instead of the equation being y equals f of x and the point being the point xy, we're talking about the set of points r theta that satisfy the equation r equals some function of theta. Let's take a look at an example. We'll look at the graph of the function r equals 3. And that will be the set of all points r theta where r is equal to 3 and theta is anything, which simply looks like this. It's the circle of radius 3 centered at the origin. And it's worth noticing how simple the polar coordinate curve equation is, r equals 3, when compared to the equation for the same curve in Cartesian coordinates, x squared plus y squared equals 3 squared. Okay, you try this one. Take a moment and see if you can sketch the graph of the polar curve theta equals pi over 6. So pause the video, think about it a little bit, and when you're ready, start it back up again. And it's the set of all points r theta, where theta is pi over 6 and r is anything, which is this line through the origin at an angle of pi over 6 with the positive x-axis. Okay, let's take a look at one that's a little bit more interesting, the curve r equals theta. And this would be tricky to sketch in the Cartesian coordinate plane that we've been using, and so we bring out what you might think of as polar coordinate graph paper, where we have units of length along the polar axis here, so that's a length of pi over 2 and a length of pi, etc. And then we have different angles theta along the outside. Here's pi over 6, pi over 3, etc. And here's what the curve looks like. When theta is 0, r equals 0. That gives us this point right here at the pole. You can see when theta is pi over 2, r is also pi over 2. That's this point right here. When theta is pi, r is equal to pi. That's this point here. And I'll go all the way up to when theta is 2 pi, all the way around the circle. Then r is also 2 pi right here. And then it keeps on going, spiraling outwards forever and ever and ever. Okay, let's look at a slightly trickier one. The curve r equals 1 plus the sine of theta. In order to figure out what r should be for various values of theta, it helps to look at the curve y equals 1 plus the sine of x in Cartesian coordinates, because that one's easy for us to draw. And that shows us that, for example, when theta is pi over 2, r is 1 plus the sine of pi over 2, which is this point right here, or 2. And so we bust out our polar coordinates graph paper. And you can see in the upper right, in that green section, what happens as theta goes from 0 to pi over 2. Well, as theta goes from 0 to pi over 2, r goes from 1 to 2. And so here we have when theta is 0, r is equal to 1. When theta is pi over 2, r is equal to 2. And you can see that it's progressing from that one point to the other point in a nice smooth fashion, just like the curve of y equals 1 plus the sine of x is. Moving along, look in the upper right again, and you can see that as theta goes from pi over 2 to pi, r should be going from 2 back down to 1. And that's how I've continued the curve here in blue. As theta goes from pi over 2 to pi, r is going from 2 to 1. Moving right along, we see in the upper right that as theta goes from pi to 3 pi over 2, r goes from 1 to 0. And that's what we've shown here as theta goes from pi to 3 pi over 2. And finally, looking in the upper right again, we see that as theta goes from 3 pi over 2 to 2 pi, r should be increasing from 0 to 1. And that lets us complete the graph of the curve. As theta goes from 3 pi over 2 to 2 pi, we see r increasing from 0 to 1. This curve is called a cardioid, Musicians might be familiar with it. It's very common to build microphones with a cardioid sensitivity pattern so that they pick up more sound from the front of the microphone and very little sound from the rear of the microphone, and that way they don't get feedback from the monitor speakers that are often positioned behind the microphone. We'll just look at a few others. Here's the graph of the 4-pedal rose. R equals the cosine of 2 theta. And if you wanted to sketch it, you could do just what we did for the graph of R equals 1 plus the sine of theta. You could do something in XY coordinates to help you figure out what R should be for various values of theta. And in the end, you'd get this lovely picture here. The 20-pedal rose, R equals the cosine of 10 theta. You gotta love that. This curve is called a limison. R equals 1 plus twice the sine of theta. Another beauty. And I don't even know what they call this curve. R equals 1 plus twice the sine of 5 theta is probably as good a name as you're going to come up with. Certainly a beauty. Imagine you had to come up with the equation for this curve in Cartesian coordinates. If it was even possible, it would undoubtedly be horrendous compared to the nice, elegant equation for the curve in polar coordinates. Okay, those were curves in polar coordinates, some pretty beautiful stuff. There's a homework to give you some practice on it. What we'll be moving on to next is doing some calculus on curves in polar coordinates, so something to look forward to. Looking forward to seeing you in class as well. See you soon. Bye.